So what we have here is an inclined plane problem to do. I'm going to start by drawing the inclined plane. I have a ramp going down at some angle. And this bottom line here is to establish what horizontal is. I'm going to label the angle of the ramp as theta. So now what I'm going to do is put a little box going down the inclined plane. Let me put the arrow to represent the weight vector. Now the normal force is perpendicular to the surface, so I'm going to use my right angle ruler to help me out with this. Usually we would have a coordinate system that has the x-axis aligned with the horizontal and the y-axis aligned with the vertical. The problem is the direction of motion is going down the ramp in this direction, which means if we want to keep this old coordinate system, we would have to break this motion up into its components. Also, you would have the normal force going into perpendicular plane, and you would have to break that into its components as well. We don't have friction in this case, but if we did, it would point in this direction, and that would have to be broken down as well. We don't want to do that, so what we're suggesting is to rotate the coordinate system this way. If we do, this normal force is purely in the y direction, and we don't have to worry about its components. Also, the direction of motion is purely in the positive x direction, so no trigonometry is necessary. And the friction force is perfectly aligned with the x direction. So rotating the axis is really the thing that makes sense for us. It's the thing that's going to make everything so much nicer. If this rotated coordinate system is confusing to you, and you're used to seeing coordinates as horizontally and vertically, you can always tilt your head at an angle theta to the side. Here, let me help by rotating the video. In fact, if you look at this, it looks like the problem we solved right before this video. Do you see how I did that there? In fact, once we get this coordinate thing worked out, the problem that I'm going to ask you to solve is actually similar, but easier than that of the precursor problem that we did before. Anyway, back to the task at hand. The issue that arises when we rotate the coordinate system is that the weight vector, which was previously aligned with the vertically y-axis, is now at an angle relative to the new coordinate system. So we're going to have to break this weight into its components. Let me draw those components for you now. Here's the component that goes along the y-axis, and here's the component that goes along the x-axis. I'm going to label the one that goes along the y-axis as W perpendicular, as denoted by a W with an upside down subscript capital T. The component of weight that aligns with our new x-axis is what I'm going to call W parallel, as denoted with a subscript with parallel lines. It looks like a small 11. Sometimes I call these W sub y and W sub x. The angle that we need to figure out is the one right here. I'm going to try to convince you that this angle between the new y-axis and the weight is actually the same as theta, the angle that the incline is. Now there's a real mathematical, rigorous way to prove this using geometry, but there's also a way to show you this using pictures and logic. The method I'm going to show you is the latter, the one with pictures and logic. So the first step I'm going to do is focus in on the object and move the traditional coordinate system over to where the object is. Let me draw in those lines just for reference. Because of a geometry rule called corresponding angles, the angle here is theta. Now what I'm going to do is sweep the coordinate system along this angle, but I'm going to rotate it about the origin. As the angle sweeps across theta, the bottom angle sweeps out the same angle. And you can see that as I rotate the coordinate system exactly by the amount theta, so the x-axis aligns with the surface, you can see that the angle x sweeps out is exactly the same amount that the y-axis sweeps out. This should convince you that this angle here is actually theta as well. I'm going to redraw that slanted triangle on the side here, just so we can see things a little bit easier. To figure out W perpendicular and W parallel, we need to use SOHCAHTOA. This means that the sine of theta is equal to the opposite over the hypotenuse, which in our case, W parallel over W. Solving for W parallel, you get that it is equal to W sine theta. Cosine is adjacent over hypotenuse, so W perpendicular is equal to W cosine theta. Here, let me draw this in the picture for you. And that, my friends, is exactly how you break down the inclined plane problem.